students, welcome to the next session. Okay, in our previous session, okay, we started with primality testing. Okay, to check if the number is prime or not. Okay, so we have learned what in that algorithm we have learned whether to check whether a number is composite. Okay, so what was the algorithm that we have used to check whether it was composite was your condition should be the principle that was x square should be congruent to y square mod n, and your x should not be congruent to plus or minus y mod n. So now today we are going to learn one more algorithm which is called as Fermat's primality testing. We say it by name that it is Fermat's primality testing, but actually it is checking for compositeness only. Okay, so the algorithm name is Fermat's primality testing because we are using Fermat's theorem over here. We have already learned what is Fermat's theorem. So what is our Fermat's theorem? Fermat's theorem says that a raised to p minus 1 should be congruent to 1 mod p. This p is nothing but your prime number. So we are little modifying. We are actually finding the same thing whether a raised to p minus 1 is congruent to 1 mod p and checking if it is prime or not. If this condition satisfy or this particular condition satisfy, then we can say that your number can be probably a prime number. Okay, so it can be probably a prime number. So basically what we are doing over here is it is not 100% sure in this method that if you satisfy this equation, that means your number can be a prime number. It is not sure 100% that it will always be a prime number. So we will solve a few more problems. Okay, so even if when it is a prime number, it shows even if it is a not a prime number, sometimes it might satisfy the equation. So let us go to the principle of Fermat's primality testing. Okay, so let n be a number of which you need to find out whether it is prime or not. Will be a number which is definitely greater than 1. Okay, because if you need to find out the factors of it, it should be greater than 1. Okay, and choose a random integer a. That a is nothing but this a, which will be provided to you in the problem. Okay, in between the a value should always lie in between 1 to n minus 1. Okay, okay, and what are we doing now? So the condition is nothing but a if a raised to n minus 1 is not congruent to 1 mod n. So this is nothing but exactly opposite to this. Okay, a raised to n minus 1. In place of p, we have taken it as n. A raised to n minus 1, if it is not congruent, if it is congruent, it means what? It is a prime number. It can be probably a prime number. Okay, it is not 100% prime number. It is can be probably a prime number. But if it is not congruent, then what we can say? Your n is a composite. So it's very simple. We are just the naming which is being given to this algorithm as Fermat's primality, because we are doing exactly opposite to check whether a number is composite. Okay, because we can 100% sure if it is not congruent to 1 mod n, if a raised to n minus 1, we can 100% say that it is a composite number. But if it is congruent, it probably be a prime number. So what we will do is I will solve one simple example, and I will give you a lot of examples to solve in this session only as a homework problem, so that you can know better what is Fermat's primality testing. Okay, so the first example that we are taking over here is nothing but we will take the previous example only, where we have taken n equals 35. In our last example, we have taken n equals 35 and a value is given to you as 2. Okay, so what we are doing over here, we are just directly substituting in the formula. Formula is nothing but a raised to n minus 1. Okay, first we need to find out whether it is congruent. If it is not congruent, then that means that what? It is a composite number. Okay, it is not a prime number. Okay, so a raised to n minus 1 is nothing but a is 2. 2 raised to 35 minus 1, n is nothing but 35 minus 1 is should be congruent to 1 mod 35. Okay, n is nothing but 35. Okay, so 2 raised to 34, 2 raised to 34 should be congruent to 1 mod 35. So how can we solve this problem now? What does this mean, 2 raised to 34 congruent to 1 mod 35? This means nothing but, okay, 2 raised to 34, okay, 2 raised to 34 mod of 35, mod of 35, I should get remainder as 1, correct? I should get remainder as 1. This is the meaning of this particular equation. 2 raised to 34, that is nothing but this. 2 raised to 34 mod of 35, I should get the remainder as 1. I have already explained you this when we were doing modular exponentiation, when we were doing the previous algorithms. Okay, so now how will I calculate this 2 raised to 34 mod of 35? How will I calculate this 2 raised to 34 mod of 35? We have already done modular arithmetic, so modular exponentiation, because it's a bigger number. To the 2 raised to 34, you will get the answer in terms of e when you solve on the calculator. So how can we solve it? It is basically using modular arithmetic. So I want you all to solve using modular arithmetic and let me know what is the answer of 2 raised to 34 mod of 35. I want you all to solve what is modular exponential of 2 raised to 34 mod 35 and tell me what is the answer. Okay, so we will just break here for 5 minutes. I want the answer and check whether that answer, whatever you're getting, the remainder is 1 or not. Okay, so check that and let me know whether the remainder is 1 or not. If the remainder is not 1, that means what? That means this equation is not, this particular congruence is not equal. It is 2 raised to 34 is not congruent to 1 mod 35. That is what we are doing in our equation. A raised to n minus 1 is not congruent. That means that your number 35 will be a composite number. Okay, so solve it. We will break here for 5 minutes. Okay, solve it and then we will continue. So when I solve this, I get 2 raised to 34 mod 35 answer as 9, which is not equal to 1. Okay, that means what? Therefore we can say that a raised to in place of a we can directly write down now 2 raised to 34 is not congruent to a 1 mod 35. Okay, when we say that it is not congruent to 1 mod 35, we can go to the principle back. Okay, therefore we can say that therefore 35 is composite. 35 is composite. Just verify in the last equation what we have done in the last problem that we have done to check the compositeness. 35 was also a composite number because we know what are the factors of 35. It is a smaller number which we have taken in the example. That's why it is easy to identify whether it is composite. But when you solve now examples which are having more than little complex value, okay, to check whether it is composite or not, okay, you will be more confident when you solve that. So 35 is having two factors, 7 and 5. Okay, so similarly I will give you few problems for homework. Okay, few problems you can solve for homework, as in you need to solve it at the end of the session. Okay, so and you can take as 15 and you can take value of a as 2. Usually if a value is not given to you all in the problem, please try to take 2 only, because it can be any number. A can be any number which will lie from 1 to n minus 1. Okay, so first problem is n is equal to 15, a equal to 2. Second problem you solve n equals 29. Okay, so for all this problem you will need modular exponentiation. Okay, all Euler's theorem to find out the answer of bigger factors like this. Okay, 2 raised to 34 mod 35. So please revise those concepts what we have done. So third problem that you can solve is 271. Okay, so n value, now see, now it becomes too much complex. 271, now can you know whether this 271 is prime or not? No. So but always remember, in this method you can find out whether a number is composite or not. But if you satisfy the equation and if you find out if you satisfy this equation, a raised to n minus 1 congruent to 1 mod n, then we can say that a number can be a probably a prime number. So you have to always write down that the number can be a probably a prime number. Okay, so one more example you can take. So one more example over here is nothing but 561. Okay, n value is 561 and a value equal to 2. So these are the four problems you need to solve and tell me the answers. Okay, now, okay, at least you can solve first and the second one. Okay, and tell me what is the answers of this, whether they are prime number, whether 15 is prime number, 29 is prime number, 271 is prime number, or 561 prime number. Okay, so in the exam they might ask you using Fermats using Fermat primality testing, check if the number is prime or not. Okay, so accordingly you have to solve the problem. So this is all that we have for today's session. This is a very simple algorithm. Okay, so basically it is given Fermat's primality testing only because we use the Fermat's algorithm in a opposite way, non-congruence way. Thank you.